So capturing a supermassive black hole is truly an incredible and challenging accomplishment here, because we know that to determine a black hole here, like for example our own black hole, we use observatories and with a lot of data and simulation, but being able to not only figure out this massive black hole using telescope, but most importantly that far away, pretty much to the early universe, is truly an incredible feat here by this team here led by Stephen Fackenstein at the University of Texas in Austin. And this here combines not only the power of James Webb Telescope's near-infrared camera with that of its mid-infrared camera, but also spectra, where we are showing different transmission, absorption spectrums, and how this comes together to produce 3 images of black holes. And not only black holes, but one that is a little bit small, but the other one that has 2 massive black holes. The smaller black hole actually reveals one that is pretty much at the early universe, that is at the region of the CEERS 1019. Now, in terms of the meaning of the CEERS, this stands for Cosmic Evolution Early Release Science, and this here is a survey technique that combines those techniques that we just addressed previously, and that number is designated to be the different segments of these images that are patched together to produce this overall image with some black backgrounds in there. So this is really fascinating to see how this technique not only reveals the earliest black hole that is pretty much around the year, I would say around 550 million years after Big Bang, but also 2 black holes that are 1 billion and 1.1 billion years after the events of the Big Bang. Now, in addition to this incredible result here, Webb was able to produce and identify 11 galaxies that are around 470 to around 675 million years old, and that is after Big Bang. So this is really an incredible result here, and looking at the details about these results includes the following. Now, looking at the graphic illustration here, in terms of the graph shown by this particular website, it shows relationship between the black hole mass, which is equivalent to solar masses, to that of the age of the universe in years. And what they figured is that James Webb Telescope was able to detect the one that is further, and this here is closer to the early universe, around 570 million after Big Bang, and this here, which is CEERS 1019 galaxy that contains a black hole, shows that the black hole's mass is around 9 million solar masses. Now, other telescopes were able to detect the other galaxies, black holes, in this case the one with the CEERS 746 and also CEERS 2782, and those 2 black holes here that are detectable by other telescopes were actually at the region of 1 billion to around 1.1 billion respectively in terms of the age of the universe, and this shows their masses to be around 10 million solar masses. Now, this here is incredible how they're able to notice some interesting characteristics in terms of the look of the black holes, especially looking at the CEERS 2782, which shows a form of a ring that is around this particular black hole, and this here implies the number of particles that are lit up or that are ingested by this black hole. And this here, alongside other incredible results here concerning the amount of particles that these black holes are ingesting, is truly fascinating how active they are. and how small they are. Now, to put things into context, it says that the JWST 1019 is having its black hole to be roughly the size of our own Milky Way black hole. Now, to show the incredible sensitivity of the James Webb Telescope, it says that this particular JWST 1019 is far lighter than other black holes that are around the early universe, and showing how less bright it is compared to other black holes that are way brighter, shows that the brighter ones tends to be really heavier, that is around 1 billion times the mass of the sun. And so this here, it shows that particular incredible sensitivity of James Webb Telescope being able to detect this incredible hole here at the earlier universe compared to other ones that are called behemoths, as it's called here in this article. Now, looking at the cosmic evolution early release science survey for the black hole that is 570 million years after the Big Bang, this actually shows the redshift here in regards to how long the light was emitted in terms of the result here. And it says here in the particular image that it is emitted around 13.2 billion years, so pretty much around 570 million after Big Bang. And so looking at the details in terms of description, it says here that at top right is a very small zoomed out version of the complete galaxy field, and to its left is a zoomed in area, and this shows an assortment of galaxies but has an insert box singling out 3 red dots. Now it shows a black hole from 13.2 billion years ago, and this here is the bottom that shows a line graph with data from James Webb's near-infrared spec. It plots wavelength of light in microns on the x-axis and relative brightness of light on the y-axis. Now, Webb's data is shown as an uneven white line and fitted to 2 different models. Now, one is a smooth purple line with a large peak that represents slower gas in the galaxy, and while the other is a smooth yellow line with a small peak representing a fast gas along or around the black hole. Now this here is in comparison with the other 2 massive black holes that are 1 billion years and 1.1 billion years after the Big Bang, and this states here based on the spectra that the 2 white lines from the image connects to pull out that run to the left of the 2 graphs at the bottom. Now in the inserted image are blurry red dots. Now the top one reads the 12.7 billion years, and the bottom area reads the 12.8 billion years. Now to the right are 2 line graphs corresponding to 2 highlighted black holes, and they are labeled the near infrared spec microshattered array spectroscopy. Now this shows the position of the emission spectrum that reveals the presence of hydrogen, oxygen, helium, iron, and this here is just for the 12.8 billion years ago galaxy that has that black hole, and while the one that is the 12.7 billion years ago is showing just hydrogen, helium, iron presence in there. So this is incredible to see how active these galaxies are, and showing that particular presence of matter that it is ingesting and also emitting is truly fascinating based on the results that we have in comparison to the earlier one. Now the earlier one doesn't show what type of elements are detected there, so I'm really interested to see how that is going to be different from what we have right here. Is there any correlation between heavier elements compared to lighter or slower gases? We don't really know at all. So it's going to be interesting to see this here in the future in terms of exploring more about the earlier black hole after the Big Bang. In addition to these three massive black holes that we see here, there are other ones that are actually shown earlier, around 13.3 between 13.2 billion years ago. And so these other black holes that are distantly early universe, they actually show a spectrum that shows hydrogen and oxygen presence. And so this comes to mind. Does that show that the galaxies that have black holes that are much later, they actually show heavier elements like iron presence? That is an hypothesis definitely that we can keep in mind in terms of how is these early black holes compared to the black holes that we have that came up later after the Big Bang. So really interested to see the comparison here in terms of the results, mainly looking at the spectrum and also the different redshifts that are resulting from these particular results here. So overall, I hope you found this really informative in terms of the incredible result by James Webb Telescope about the detection of these supermassive black holes. Not only the sizes of these black holes, but also the contents that they actually have here with regards to what type of matter they are ingesting, and also what impact do you think that this might have in terms of our understanding of our own black hole in our Milky Way. All the same, see you on the next video. The links are all in the description box, but that way we can talk to you soon. Stay smart as always and believe in yourselves.